Okay, so let's see what general rules now we can begin to draw from this. So let's take a look at here now, field line rules for conductors. And there are going to be 5 of these, just like we had 5 rules, general rules for field lines. So the first rule is something that, as you can see from our discussion, occurred over and over again. If we look again at what had happened, you'll notice that whenever I had a field line in the conductor, either when it was at the very beginning of the problem, at our initial guess, right, or when I was considering whether I could have a positive charge inside my conducting region, immediately charges started moving around to cancel out any of those field lines, because we know there can't be any density of field lines in the conductor because the electric field has to be 0, and if there's no density of lines, that means there are in fact no lines inside the conductor, which is what we finally came down with in our final conclusion. So our first rule for field line rule for conductors is that there can be no electric field lines which we'll just be calling FL for short, inside the conductor. That's our first rule. The second rule then has to do with a consequence of this rule, really. And that was the second thing that we were at some pains to really understand well, which was, well, not only notice were there no field lines that ended up here inside of my conductor, right? There were no field lines left over, but also there were no charges, no uncompensated charges in the interior of the conductor, right? We thought about what would happen if the positive charges that were left over from the motion of the negative charges ended up inside my conductor, but we realized that would imply the presence again of electric field lines in there. The only way to avoid electric field lines inside that conducting region is to make sure that none of the charges end up inside the conductor uncompensated. The same thing, by the way, works if I imagined, what if I had a region where there was an uncompensated minus charge? Now, by uncompensated, remember, we have to keep in mind, in the interior of the conductor, there are, of course, many, many atoms distributed all over the place that are made out of little positive nuclei and negative bound electrons, right? There are always charges in here, but they're always in perfect balance. You can't have an unbalanced minus charge like this either, because if there's an unbalanced minus charge, we know there have to be field lines ending on it in proportion to that charge, so that would imply, again, that there were some field lines, but if there are field lines inside my conductor, I've got a problem. They're going to be compensated out very, very quickly, so that situation just can't happen. So our second lesson from this is that there can be no, and I just put the proviso, uncompensated charges in, and this next part is key, in the interior of a conductor. Right? Because what we saw was, well, those extra charges that came from the minuses did not end up anywhere inside the conducting material, right? They ended up there distributed out towards the outside on the surface. I want to stress, though, here that when we say interior, right, I'm talking about in the material itself. We will see situations such as the situation you see right here. This hole here, right, you might think of as the interior of this conducting ball, yes, but it's not interior to the material itself, right? It's a vacuum region, and that's why I'm allowed to have these field lines here. It's only inside the material itself, so only in the interior material of a conductor. Maybe I better insert that material just to be extra clear about what I'm saying. Okay, now, the next conclusion we came to was, well, those extra positive charges couldn't have be in the inside. They must only be existing on the surface. The surface was okay because then you could expel the field lines to the outside and not be stuck with any field lines inside the conductor. So that's really the third lesson here that we can draw from this, is that all of the, of course, uncompensated charges end up on the surface. Of the conductor. And those are really the main lessons, the first three here at least, of what we can learn from our experience on this one specific problem that we can draw out, right? There are two now additional rules that deal with this question of what happens to charges on the surface. How do they distribute themselves, and in particular, what happens with regard to the electric field lines near the surface of a conductor. So I'm going to leave space here in our field line rules for two more rules, 4 and 5. And now we're going to think a little bit about charges on the surface of a conductor and see what general lesson comes out of our considerations, and then we can include those lessons in here as our final lessons for the field line rules for the conductor. Okay, so now here I just want to consider sort of a general situation near a conducting surface. Okay, so field lines near a conducting surface. So I'm going to imagine some conducting surface, some generic surface. I guess I'm going to let it be a little bit curved here, something like this maybe, right? Some surface. I've got this conducting material down here, and on my surface maybe I've got a bunch of positive charges collected here, 5 of them at a certain region, and each of these of course then have to be attached to a field line. Just imagine these here are actually all directly on the surface. They're attached to a field line, and the field lines maybe are coming off of the surface like this. We know that these field lines have to be on the outside of the material region of the conductor, right? There can be no field lines in the interior parts of the conductor. I'm just sketching my conductor here a little better. There can't be any field lines on that interior side, so they have to be expelled outward. The question, though, is now, well, what direction can they point in? And there's something very interesting if you consider the scenario that I've shown you here. Remember now what the electric field lines, what their direction tells you. The direction of the electric field line tells you, of course, the direction of the electric field. And since I've got these positive charges right on that surface, they are feeling forces, because they're positive, in the same direction of the electric field. So they are all going to be feeling forces under a scenario like this, off in this direction that I just happened to pick. Well, now, that's interesting, right? Because we know the charges in a conductor are free to move, and we might begin to wonder, well, this doesn't look like the settled down equilibrium situation, right? There are forces on these charges. These charges are going to want to move. They're not just going to put up with that. Now, and in the conductor, they're free to move. Of course, you can think about it's actually the negative charges in most metals, and they just be moving in the opposite directions from what I've been saying. But I hope by now we've gotten used to this idea that you can think of it as either the negatives or the positives, which are the moving charges. You will come to the same conclusions in the end. It's just easier to think about the mobile charges as though they were positive. So if this were the situation and these were positive charges, they're free to move, but there are some constraints, right? The force is trying to, here as you can see, pull them directly off of the surface. Well, if the electric field is strong enough, it might actually be able to rip charges out of the surface. But the truth of the matter is, for most normal electric field strengths, right, the conductor has interior material forces that we're not talking about here due to the quantum mechanics and the bonding that goes on inside of the material that help the material hold on to its charges. So they simply can't just leave the surface. On the other hand, they are free to move as much as they would like within the surface. So what one would have to do then is to look at the electric force, right, which is directed upwards like so, and to break it into its components. So let's consider the forces on this particular positive charge here. And we can imagine that we're breaking them then into their components, so it'll have one component here along the surface, one component perpendicular to the surface. And what we are saying here is that there are interior material forces that are pulling that positive charge down to keep him inside the surface. He can't move outward. What's left of his force, however, is this horizontal force along the surface, and he's certainly free to move in that direction. So let's consider what happens then as these positive charges, at least some of them, begin to move over in this horizontal direction. So that now I'll end up maybe with some positive charges beginning to collect over here in this region. This, of course, is going to change the electric field pattern. Right now, there were, some distribution of charges leading to electric fields pointing off in this direction. These charges over here now are going to produce their own electric field, which is going to be directed, I'll draw it here in a dashed line, but the electric field that are contributed from these particles then will tend to point off in this direction. And what I hope you can see is that when I add this arrow, right, from the original electric field to an arrow in this direction, you know how you add them head here to tail, the sum, say, of this vector and this vector would be a much more upward pointing vector. So the process of moving the positive charges in this direction all tends to push these electric field lines so that they become more straight. But and you can see that process is going to continue, and if they're still tilted over in this direction, I'm still going to be gathering more and more positive charges over here until I get to the very happy situation, right, an equilibrium situation where now I've gathered as many positive charges over here exactly as are necessary to push these field lines over into this direction until I reach equilibrium, until things stop trying to move. And that situation then would look something like this. So up above here, I have the beginning, the start situation. And then down here, I could have the end situation. And in the end situation, I'm going to try to draw the same sort of arc as the shape of my conductor. I've got this material, and the positive charges now have redistributed themselves in some nice pattern, like so, and the electric field lines now are pointing directly perpendicularly from the surface. It has to be perpendicular. If they are not pointing perpendicularly to the surface, there will be some component, either to the left or to the right, that would then tend to drive my charges to one direction or the other until they are able to straighten up those electric field lines. So, our fourth lesson here is that the field lines, the FLs, are always perpendicular to the surface of a conductor, to a conductor surface. Now, our fifth and final rule then has something to do with the strength of the electric field as we come to the conductor surface. We know something already, I think, right, about the electric field, the strength of the electric field, which I think is very intriguing when we begin to think about what happens when we are near a conducting surface. If you recall what we had said previously, we had said a couple of things. We had said, right, that the number of lines per unit area is proportional to the electric field. So I know that the strength of the electric field here, at the surface is going to be proportional, so it's a vector, and I'm talking about the magnitude of the vector. That's going to be proportional to the number of lines per unit area. But let's think now what we know about number of lines and see how we can link that to our charges. We've already been through in our original set of field line rules that the number of lines entering a charge or a region is proportional to the number of charges that are there. So that is telling me that the electric field surface strength is proportional to the number of lines per unit area, but lines per unit area is equal to, in fact, the lines themselves. I shouldn't say equal. I should say proportional to. Right? They are. Here, let's make this back to a proportion. Whoops. Those then are going to be proportional to, because the number of lines are proportional to the charge, and the area, of course, is the area. But charge per unit area, we know, is the variable we usually call sigma. That's the surface charge density. So we have this nice relationship that the strength of the field near the metallic surface is proportional to the surface area. So we know something about the direction has to be perpendicular of the electric field, and now we also know something about the magnitude of the electric field. It has to be in direct proportion to the concentration of the charges here on the surface. So that's great. That's a powerful statement of itself. I'd like to take it now one step further, right? That's kind of like the qualitative statement. This gives us an idea, sort of, of the difference between, say, philosophy and physics. You can get very far with just basic thinking and the methods of philosophy. What really has to make a rational description of the world around you. And as we saw in earlier examples in the course about Empedocles and so forth, and also Descartes and how his Cartesian vortex idea was very close to the modern idea of a field theory, and we'll see a little bit more of that in these notes coming up. You can get quite far that way, but you can't really get all the way. Well, I want to go a little further than from just this sort of qualitative statement that the electric field is going to be the field strength is going to be proportional to the surface charge density. I want to go to the next level. I want to figure out this proportionality constant. So, if we're going to do that, we now have to get quantitative. What equation can I use in order to make this direct link then between electric field strength and surface charge density? Well, where should we begin with this? In mechanics class, you might recall you always had a in mechanics class you recall you always had a backup plan, right? If you ever get stuck in mechanics class and you don't know what to do, think about it. What is it that you write down and you begin working with? You always go back to F equals ma. Now, in this class, what should we go to? What is the F equals ma of electromagnetism? Well, it turns out we have sort of 4 different equations we can play with. There are Maxwell's equations. And you guys have now, at this point, learned just one of them. And that's what our fallback position has to be for now, until we start learning other Maxwell's equations. And the Maxwell equation that you know is Gauss's law. So let's try to apply Gauss's law to this specific situation in order to answer this generic question of what is the quantitative relation between surface charge and electric field strength. So we're going to move up half a page here and see if we can do a Gauss's law analysis. Okay. So the idea is we're going to apply Gauss's law. Now to do this, remember our basic rules. We want to make a judicious choice of Gaussian surface. We want a surface that is going to be always perpendicular or parallel to our field. We've got a nice sketch of our field. It's always perpendicular to the surface. And it has to include at least some of the charge distribution of interest. In this case, that's going to be these surface charges. So it turns out then we can come up with pretty quickly a very nice shape for this. It's something that's called a Gaussian pillbox. It actually looks like one of those mints you might buy at the gas station. Right? I want my surface to be always parallel or perpendicular to these field lines, so that's easy enough. I can take something maybe that has a circular surface here that's running nice and perpendicularly to these field lines. And then I can continue my surface down like a little very thin can, kind of like a tuna fish can, into my metal surface. I want to go down like that to make sure that I'm capturing some of the charges here on the surface. And I'll have nice, straight, parallel walls to my can so that they run perpendicular to that electric field. And then down below, I have to make it a closed surface, so I would close off my can like so. And with a bottom closed surface, and keeping in mind always that as this can crosses the actual surface of the metal, I'm going to be trapping a certain amount of this surface charge. So there is going to be a region in here of surface charge that I've captured as well. Now let's put, it's always good to quantify our Gaussian surface. So I'm going to call the area of the top and bottom, I will call that A. That's an arbitrary trace that hopefully will cancel out. And also, in case I need it, I can refer to the height of my little tuna fish can. I will call that H. So we've chosen our surface. The next part of our analysis, as you know, always is to write down Gauss's law in our preferred form, which is to say that the enclosed charge divided by epsilon naught is going to equal the closed surface integral over our can of the electric field dotted with the surface area vector. So now we go about evaluating both the left and right-hand sides of this relationship. In this case, in terms of the enclosed charge, there are no charges, in the vacuum region above my metal, or the air region. There's no charges in the interior of the metal. That's one of our metal rules. The only charges are on the surface of the metal, and they are all concentrated here in this circular cross-section of my can, right, that has an area A, and I'm supposing I have a certain surface charge density here, sigma surf. So I know then that in terms of the enclosed charge, it's the surface density times the area, and I'm substituting in, so that divides by epsilon naught. Very good. And now I have my surface integral. And as you guys know, the best way to do this is to break it down into its component pieces of my surface. And I've got different types of regions, of course, on the surface. I've got the top and bottom of the can, and I've got the sides of the can. So it's going to be integral around the top of E dot dA. Now the top by itself is not a closed surface, so I don't put the closed surface symbol on it. I've got the bottom of my can, integral E dot dA. And then I've got the sides of my can. The circuit, the curved outer side of the can. And that's integral E dot dA. Next, what we like to do, once you kind of get the hang of this, is we should quickly recognize that if we've chosen a judicious Gaussian surface, that a number of our component integrals should be vanishing because things are always perpendicular or parallel. And if you think about it here, let's look at them one at a time. Okay, the top surface, well, that's got electric field lines going through it, right? In the mechanical fluid model, that would correspond to an actual flux of liquid leaving my surface. That is going to give me some contribution. That's not going to be zero. We better come back to that one. When I go to the bottom, the nice thing is we are inside the metal, and we know that inside the metal there is no electric field. So the electric field here is 0 inside the metal. It's 0 inside the metal, or the conductor. So we know that whole term is going to vanish on us. We don't have to worry about it. For the sides, the nice thing is, again, the fluid model really makes this kind of easy. On the sides, the field lines are always parallel to those sides. There's no fluid that actually ever leaks through those sides. That's because of the cosine of our angle. You could think of it either way. It's going to vanish. There's no flux, right, or no flow across the surface. The other way to think about it is, well, the normal to the surface is horizontal, whereas the field line is perpendicular. So those are at a right angle, and I know there's a dot product that will have a cosine, and the cosine of 90 degrees is going to give me 0. Either way, this term also vanishes, and I'm left to concentrate on the top surface. Now, the next rule, and I always try to be very careful. I know some of you might think I'm overly pedantic on going through all these little steps, but I want to assure you that I go through all these steps myself too. The reason is that over the years, I know where I make my mistakes. And the most common mistakes are forgetting some niggling little detail about the vector directions. So I like to make sure I've accounted for everything. I write things out very carefully. So I'm going to rewrite my integral. So this is an integral. Let's move the screen up a little bit. Over the top, the dot product is the magnitude of the vector E, right? Dotted with the magnitude of the area vector, dA, right? Times the cosine of the angle theta between them. And now I can go and think about what these quantities are. If I look at my diagram, right, dA, that's just going to give me, the dA vector, its magnitude will just give me dA, right? That's just the magnitude of the area element. The angle theta, well, now I'm talking about the angle between this electric field, which points straight up. And if I want to think about a little dA vector, it has to be perpendicular to my surface, right? And that dA vector is going to be very nicely parallel, in fact, to the electric field vector. So the angle between them, between dA and the electric field, is 0. So I have cosine of theta. Cosine of 0 is equal to 1. So I don't have to worry about that term in the product. And finally, the electric field magnitude that I'm looking for, that is just, the question I'm asking. That is the surface strength of the electric field. So let's just write that for short E surf with no vector on it, because I mean that to be a magnitude. Now, finally, having considered all the quantities, I can then finish off my integral. So I've got integral over that top surface of the magnitude of the field at the surface. The cosine theta went away, and it's just an integral dA. And now let's look a little more closely at what we're doing. The name of the game here is going to be, I want this actually, I've drawn it somewhat tall. I want to take the limit here, right, that h goes to 0. I want to make this thing actually a very small and tiny box. I want to really kind of move up this bottom portion, right, and move down the top portion to make it a very thin little sandwich right hovering over that surface, so that the electric field that I'm measuring on this top part really is the electric field as close as I can possibly get down there to the metal. Also, what I will do is I will shrink this circular region also down to a specific point, so that I can compare the electric field coming into that point to the charge density right under that point. So when I do all of that, that's just a fancy way of saying I'm going to shrink this thing very small so that the electric field is going to be nearly constant over that surface, right? So it's going to be constant as I shrink to a point. And since the electric field is constant, of course, I can then factor that out. And then the integral of dA, of course, will just give me the surface field strength times the area A. And that, of course, makes me very happy, because A was something, as we said, that we just made up, right? When we made up our surface. It had better cancel out of our equation. And I've got an A on this side, and I've got an A on this side over here. I can cancel those out. So when I write down my final result, it becomes sigma surf, if you want, times A, just copying the result over again, over epsilon naught, equals E surf times A. But our hopes had come true. The A's cancel out. And our final conclusion then is that if you want to know the electric field at the surface, it is indeed proportional to the surface charge density. That's what we had expected just based on our field line arguments. But now we know the correct constant of proportionality. It's 1 over epsilon naught. So it's equal to 1 over epsilon naught times sigma. We can put a box around that. That's a very nice, happy final result. So now we can relate this back to our final set of field line rules. Now let's go up to where we had those to try to complete them. So we had that the field lines were always, the direction of the field lines is perpendicular to the conductor surface, and now we also know that the strength of the electric field, not just its direction, the strength of the electric field is given by the surface charge density of the charges gathered onto that surface divided by epsilon naught.